Hi, this is the related rates intro. So we're actually going to be doing a Desmos activity that's attached to this. So our practice and the notes really is going to be attached to Desmos in a link, and I'll explain more about that later. But I need to give you some intro before you start that activity, and that's some of the, I guess, lingo you're going to run into with related rates. And related rates problems are different than what we've done before because we're going to actually use equations like volume or area or what else is there? Not surface area, but you might see that in AP Calc if we were in AP Calc. But in this equation, or in this practice problem, we've got gravel that's being poured onto a conical pile. It's creating a cone as it grows. So its volume is going to change according to the amount of whatever gravel we pour on it. So the height also changes and the radius also change, and they're all bound together by this relationship. And that relationship is this volume. And there's going to be some things that we set up with these, and we're actually going to do these problems in class. I'll post the notes before we start, but we're going to do some problems in class together because I want to be more hands-on with you all about this. And this volume is the relationship that we're using. And one of the first questions you'll be asked on this Desmos activity is how do we represent this derivative? How do we represent these things, volume, radius, and height changing? So we want to know how they change with time. So this is critical here, and my mouse is not drawing. There we go. How these items, volume changes with time, height changes with time, and radius change with time. So we're going to take the derivative with respect to time, which time we're just going to represent with t. So d dt, and there's my mouse skipping again, of the entire equation. So we'll just split this up into the derivative with respect to time of volume and the derivative with respect to time, with respect to time of 1/3 pi r squared h, which is the volume of a cone. So that's why this relationship is important. When you're given these problems, we aren't going to have to know these equations of volume, or, you should know the area of a circle or the volume of a cube, but some of these more obscure ones you'll be given. So the way we find the change in velocity over the change in time is with derivatives. That's why we're taking the derivative with respect to time. And not only that, but we're using implicit derivatives to do that. Now, in this problem, we have v as a variable, we have r as a variable, and we have h as a variable. Pi is not a variable. Pi is not a variable in this problem. It looks like it is because it's a Greek letter, but we all know that it means a specific number. So while this looks like a pretty complicated thing that is out in front of r squared h, this 1/3 pi is just a coefficient. So what we're looking at actually is just a product rule derivative with r squared and h. And the left side does itself. We've got the change in v over the change in time. So the velocity changes over the change in time. So we're representing that. And now we're performing the product rule. So I'm going to have 2/3 pi r times dr over dt. So I have said I'm going to do the derivative of this first thing, which let me get rid of some of these lines here. So this first thing that we have in our product rule is this whole item, is this 1/3 pi r squared h. And then h is the second item. So I've taken the derivative of 1/3 pi r squared h, and that's what I've written right here. And then I need to multiply by h, so times h. I'll try to use some different colors here so we can get some pieces identified. And then plus the whole 1/3 pi r squared. So 1/3 pi r squared. And then times the derivative of h. When it's with respect to time, so that's just dh over dt. All right, cool. So we have the relationship not only between like volume, radius, and height, but we have a relationship in terms of the derivative, so the change in volume and the change in height and the change in the radius with respect to time. So if we just have some of the data, which is what you're going to be given in some of these problems, if we just have some of the data, then we can figure out how quickly these things are changing. And right now, what we're just going to focus on is recognizing the relationships between these things. So this is just going to give us a grounding spot for class when I see you on Friday. So here's that problem in the Desmos activity. You'll see it, and you'll find the right answer here. So we've got a 1/3 out in front, so you'll have to figure out which one of these is going to look like the one that we just talked about. And it'll record your answer. We'll get to use it as data in class. And then it starts talking about some different examples. So it gives you the like a snowball example. It has some like different graphics for you to look at and think about what two things are changing with respect to time. All of these are going to be with respect to time. And you can kind of witness these items changing on the there you go, on the video. We've got some more questions. There's some more. I think this one's cool, but it's a little confusing. Maybe you can tell what's happening. What they're doing is they're dropping a rock into water, and it's creating this this, what do you call that? A ripple, right? So that ripple is the thing that's expanding. So how do you represent circles expanding is what it's asking. So this is what you'll be doing, and it's just going to give you an idea of what to be on the lookout for. Just some general understanding before we start talking about the math behind everything. So do this, complete this. You can see there's 19 slides. There's some good examples in here, and I'll be talking about it with you all. So be prepared to do some notes when I see you, but take some time to do this well, and maybe put on some music or something like that, and we'll talk about it in class. So see you then. Bye.